What is a pendulum? And did it make any difference? I mean, was its discovery important? And I'm saying it was a very important discovery, okay, or development that they started working on the pendulum, okay. But before we get to that, I gotta go with the what we left off the other days, last couple times, which is this energy deal, because a lot of the folks out there, apparently they think they still haven't learned the lesson what energy is, and they just keep giving me the party line. They just put things that they copy and paste. That's all they know how to do. This is what they learned by rote in high school, maybe college, and they say the same things over and over again. They go out there and just copy and paste. They say, this is what energy is. And they don't attack the question. They don't address the issues that are being placed before them. So they're skirting the issue of energy. And I can see why, because they cannot answer the questions that I'm asking them. They're not addressing my comments, okay? And so this is, again, for those people who have a little more intelligence than some of these fellows, okay, for you to ponder, okay? Here it is. Fellow says, energy definition is what? Capacity. Okay, capacity, that's what energy is. Capacity to do work. The definition of capacity, right, to do work is what? Conceptual. Yeah, capacity is a concept. There is no physical standalone object called capacity. Okay, and as far as we know, only objects can move. Concepts cannot move. What does he say next? It says, each form of energy is explained as an entity that can be transferred, moved. So he's going to move the capacity around. Then he continues and says, a car battery has capacity. Okay, so it has capacity. Great. What does it have? It has a concept. This is different than saying, I have a coin in my pocket. That would be having a thing in my pocket. That would be a thing, right? But if I say I have a headache, that's not a thing that I possess. That's a development. That's a verb that's going on in my brain. Okay, so having a headache is not the same thing as having a coin in your pocket or having money on your hands, dollar bills on your hand, okay, or a coin in your hand. Are we starting the car with a concept? Well, no, we're starting the car with gas. Gas is not a concept. Okay, gas is a thing, is an object, a thing. Charged, the battery will have more, he said, mass than when dead. Well, he's probably wrong. He probably meant weight, because mass, I don't think he counted all the atoms in the battery. Okay, what he did was weigh it. Okay, he put it on how did he determine that the battery had a difference between before and after? Well, he weighed it. Okay, so he put it on some kind of device that measures its weight, not its mass. Mass is counting. Okay, you've got to count atoms to get to mass. It's the quantity of matter. Are we measuring what is existing only in thought as an idea, but not having a physical or concrete existence? Abstract concept? There are only concepts or objects. Okay, he got one right. The power of elimination isn't complicated between the two choices. Again, very true. Saying energy as a concept is completely ridiculous. But he's saying that it's capacity, and then he says that capacity is a concept, and now he's saying that to say that a concept is, that energy is a concept is ridiculous. So he's going around in circles, and I'll tell you why. Okay? And it's that he doesn't define the terms. He's got to define what an object is and what a concept is. He's got to tell us what the difference between those two words is before he can go around in circles like he has here. Okay? In physics, if you define a word, that term is a concept. Okay? If you define, it's a concept. If you can point to it, then it's an object. And the question is, can you point to capacity? Okay, this should be a straightforward issue. Any rational human being should be able to deal with this. And if you can't, well, you're not a rational individual. You have a problem, a mental problem. You don't have to talk about physics. You need to see a shrink. Okay, this is how simple it is, straightforward. Okay, another fella says, again, they're stuck on this energy thing. Because he, unlike this other one, he says you can point to capacity. Okay? But he's got a different idea of what energy is. He says it's not, he doesn't talk about capacity, okay? He talks about a delta. Okay, we'll see what this delta thing is, okay? Here's the process for seeing the delta. Okay, I want to see it. These are the instructions, I guess, he put in there. He says, you take your film and splice out your start frame. Okay, I did that. Took frame, even though that's not the start of my film, of my complete film, but that's where I'm going to start my film. No problem, I can have a film strip. That's going to be my first film, my first frame of the film, 505, okay? Then overlay it on the end frame, finally shine a light through it, and you're now looking at the delta. Okay, I called it the 506, doesn't matter. Okay, so I take these two, I put one frame, the 505 over the 506, which is what you see there, And he calls that the delta. And he says now he can point to the delta or to the frame or to whatever. Question is, will anyone on Earth say, oh yeah, I know what that is, that's energy. One frame on top of the other, and that's energy? Or a delta, letter D, Greek letter D, I guess, right? Is that what energy is? Would every person on Earth recognize and say, oh, okay, I see what he's talking. He's talking about energy. No, I don't think they would. No, what you need to do is present a standalone object, a mock-up of it, make it visible, put it on in the middle of the conference room. That's how we do it in science, okay? And if you can't do that, well, you don't have an object. Okay? So you don't give instructions on how to visualize energy. You make a drawing or take a snapshot or take some silly putty and mold it, and you say this is energy. This is what it looks like. That's how it works. Okay, that's an object in science. In religion, you go through all this stuff. In religion, irrationality, then you say, well, let me explain to you what energy is. No, if you can define energy, it's a concept. We don't define tables. We don't define chairs. We don't define dogs or trees. We point to them and say dog, tree, chair. That's how you present an object in physics. Not in ordinary speech, in physics. Okay? So what you have to do is bring energy, put it in front of us, a little drawing, picture, snapshot, statue, point to it and say energy. That's all we want to see and hear. Okay? Then you have pointed to energy. Right now you're going through this rigmarole. Let me point to the delta. And what is the delta? Well, you put one frame on top of the other and no, that's not science. That's religion. You're an irrational individual. Okay? The way, first, again, you got to know what an object is for the purposes of science. An object is that which has shape. And yes, if it has shape, there should be no reason for you to make a drawing or a picture or a mock-up of it of some kind and to point to it and name it. Say, tree. And then we know what a tree is. You want to explain to or identify an object for an ET, Klingon who comes to visit us, and you say tree, and you say, oh, well, what is a tree? And you say, that's a tree, and you point, and you say tree. And now he knows what a tree is because he sees it there. He says, okay, the word tree is associated with that thing he pointed to. That's how simple it is. And now you say energy, and you say, oh, what is energy? Let me explain it to you. First, let me define it. It's capacity or the delta or who knows what. And then he says, and see, this is the way you visualize it. You put one frame on top of the other, and then you shine a light through it. And the guy said, oh, okay, let me have a beer now. I need a beer. Okay, well, it says mass and weight are two distinctly different measures. Yeah, they are, but weight is a measure. Mass is not a measure. Okay, mass, you count. Weight, you measure. Okay, so weight and, measuring and counting are not the same things. Okay, you count 10 apples, and you say, those are apples. Okay, how many apples? 10. 10 apples. That's mass. That's the notion of mass. But if you weigh the apples, you say, okay, they weigh, 10 pounds or whatever. They're big enough. So weighing is not the same thing as counting. Okay, so mass is like counting apples. Weighing is like putting them on a scale of some kind and getting a number usually in terms of pounds, kilograms, whatever. We can buy in mass measures of kilogram, gram. Well, no, we call it weight. That's how we use it every day. Okay, in fact, even the mathematicians use it. We can't buy in weight measures of newtons or joules. Yeah, nobody uses newtons or joules. I don't even think mathematicians deal too much with newtons and joules, again, because they don't really deal with units of weight. They talk about mass. They talk about kilograms and pounds in terms of mass, and the way they determine that is through weighing. So they're using the word mass to refer to weight. That's what's happening. And yeah, the units are kilograms and grams and so on. Okay, so we don't use joules or newtons. In fact, when talking about energy, we used to use KeVs, kilo electron volts. So we don't use some of these units that are very specific to certain industries and certain fields of study. Okay, those are very particular. People don't even know what a newton is out there. They wouldn't even be able to define it. They don't have any idea. The way it works is everybody uses weight, calls it kilograms, and the mathematicians want to say that, well, that's really mass. But it turns out that the way they determine that mass in kilograms is by weighing, because kilogram is a weighing type of unit. It's not a counting unit. Okay? Counting is 1, 2, 3, 4, 5. 5 whatevers. 5 units. Okay? How's that? So 5 units would be notion of mass. But if you say kilogram, weighing, you're talking about weight, not mass. But the mathematicians called it weight. That's where the problem is. We can't subdivide grams into newtons. Yeah, they aren't the same kind of measure. Okay, you are using the word weight as its common definition. The physics definition is a different definition. It's interesting, they say, you got the wrong definition, but it would be nice if they put the right definition, right? And they never do that. They just say, you got it wrong. Okay, so let's put it up there so that everybody knows if I got it right or wrong. This is the definition we use, okay? Here it is, weight, mass multiplied by the acceleration due to gravity, okay? Weight, another one, the force acting on the object due to gravity, okay? Apparently weight has something to do with gravity. And what is mass? Well, here's a paper dating all the way to 1915. Mass as quantity of matter. And you see another entry somewhere in the internet. I didn't put all these references, but mass is a way of measuring the amount of matter. So what is weight? Well, any body is acted upon by the acceleration due to gravity to get the value of the weight of the body. Mass, on the other hand, the amount of matter present in that particular body. Okay? And yeah, that's the notion we have. But see, we don't count atoms, so we don't know what the amount of matter is except by weighing. That's where the problem comes in. And here you see it. Okay, this is what we have. You put the balance on the earth. Well, then, yeah, what you do is you're looking at weight, mass multiplied by the acceleration of gravity. Okay, but that's how we determine. The way we determine all these things is by weighing. Okay, we don't determine mass by counting atoms. That's the bottom line. Okay. Okay, so and what's missing there again are the ropes, but that's a secondary issue. First, we need to understand why mass and weight are synonyms in mathematics. They are synonyms. They are synonyms because when you're talking about something falling to earth, we call that weight, and the mathematicians call it mass because they say, well, it's a measure of the quantity of matter. But see, quantity of matter is not a measure. Quantity of matter is counting atoms or whatever, units. Whatever unit you want, no problem. You choose the unit, no problem. But you better count if you want to talk about quantity of matter. Quantity of matter is not measure of matter. Measure of matter is weight. Okay? We measure weight, we count atoms or units for mass. So if you're going to use the word mass to refer to whatever gravity does to a body, then you're talking about weight. And what these people are saying is we're going to call that mass. And so you have people like Einstein who goes in there and says, if an object accelerates near the speed of light, it gains mass. So what? It gained quantity of matter because it sped. Did it gain more atoms? It became bigger and bigger and bigger because it gained more atoms? And they say, no, it's because of the force with which it presses against the scale. That's the notion, right? It's a calculation, but that's the notion. Notion is pressing harder and harder, so now it gained mass, meaning it gained weight, because now you're having this thing press against a scale. That's a measure of weight, not of mass. Mass is quantity of matter. That means that if the object gained mass, it became bigger. And if it just presses harder against something, it's the same ball, but pressing harder, we call that weight. But the mathematicians called it mass, and that confuses everybody. That's where the problem starts and ends. Okay, and here you have Mr. Einstein. He came up with a principle of equivalence. He didn't understand why. He just said it seems like these two equations, mass equals force divided by acceleration, which was Newton's second law. I talked about that in the past. It wasn't probably not even his, but and Newton's gravitational law, again, probably not his. But he said if you have these two situations, they're equal. Okay, a man falling from with his elevator and rising with the elevator at given speed, given acceleration, well, they feel the same thing. And so he didn't understand why, but he said, I'll call that the principle of equivalence. And what he was saying essentially is that mass is equal to weight, because what is mass? Well, mass, if you use the mathematical formula, okay, not what it is in physics, but if you're going to use a mathematical formula, force divided by acceleration, okay, what do you have? Well, if you set that equal to Newton's gravitational law, well, now you have the principle of equivalence, okay? But what Einstein missed is that he never figured out the difference between mass and weight, just like all these people, because he was talking about weight, not about mass. He was talking about accelerating something and pressing against the scale. He was talking about what you feel if you fell with your elevator or rose with your elevator. Okay, he said the feeling is the same. Yeah, feeling we don't care because there are no observers in science. But the issue here was that he was equating these two equations, right? He was saying that the first equation is equal to the second equation. They do this all the time. And he didn't realize that what he was essentially saying is mass and weight are the same thing. Okay? That's what it came down to. But the mathematicians don't pick up on this in great measure because they use the word mass to refer to weight. That's the whole problem. They're talking about weight and they call it mass. Okay, let's move on to the what is it? The pendulum, and this has a lot to do with what we just talked about because pendulum is a gravitational device, and it takes this potential energy, whatever that is, and turns it into kinetic energy, whatever that is. Okay, we don't know what energy is, but one is transformed into the other. That's essentially what happens with a pendulum. Okay, and so it all starts around the 17th century, so-called scientific revolution. I call it the unscientific revolution. Okay, so let's start with that. And here it is, an unscientific revolution. The first casualty was Aristotle. That's the unscientific revolution essentially killed Aristotle. Okay, so rest in peace, And he died, and then what happened was they started doing experiments. They said, well, we can't do it the Aristotelian way of saying, oh, let me do a thought experiment, which was later on resuscitated by Mr. Einstein, right? He said they used to do these thought experiments, and they got a lot of those wrong, and that's why all these people criticized Aristotle. Says you should have done experiments, real experiments on these things, on simple things, right? Like throwing two stones and one big, one small, and finding out they hit the floor at the same time, that sort of thing. Okay, so they started doing experiments. Okay, actually it started really in the 16th century. So to say that it was the 17th century revolution, scientific revolution, I would say that started already in the 16th century because you had, and I mentioned some names the other day. Who was it? Moletti, Stevin, Gilbert, just a few names there, but there were a lot more people. These weren't the only 3 inhabitants in those days. There were a lot of people out there doing experiments, especially with things that Aristotle should have done, like, throwing 2 stones. A lot of people did that experiment, and it got around. Again, I talked about that in the past, but 16th century, you had like Gilbert, he played with magnets and so on, so a lot of people were doing experiments already. Okay, but 17th century really is where it took off and where you have all these mathematicians come into play and they started analyzing these things and mathematizing them, quantifying them. That's where the change in the 17th century came in. Okay, so you have a rapid evolution of math. Okay, emphasis on observing controlled experiment. No longer was it a casually observing something. Now you deliberately created an experiment and you say, okay, and you started controlling all the factors that could influence your experiment. And so experimentation improved significantly in the 17th century. In that sense, you can say it's an experimental revolution, not so much a scientific revolution, because experiments have nothing to do with science. Let me repeat that, because people say, well, you misspoke. No. Experiments have nothing to do with science. Mathematics has nothing to do with science. Science is about explaining. An experiment is not an explanation. Math is a description. Okay, so let's get it right. Science is explaining something, mechanism, especially in relation to physics. Physics is about explaining mechanisms. That's what physics is about. That's what the mathematicians who don't explain anything rationally, they dismiss that as philosophy. Okay? They say physics is math and experiment. That's essentially what came out of people like Galileo, especially. Okay? And so they established quantitative relationships in experiments. And again, it was an issue of fight between descriptions and explanations. What is an explanation? Physical interpretation, mechanism. That's what physics is about. And that's why they stopped. That's why I don't call it a scientific revolution. If anything, we got sidetracked. We went on a tangent and started doing math and experiments and forgetting completely about explanations, okay, about mechanisms. And here's Galileo's take on that. It just puts it in the right context, okay? Philosophy, natural philosophy, right? He was referring to physics, is written in the great book which ever is before our eyes, I mean the universe. But we cannot understand it if we do not first learn the language and grasp the symbols in which it is written. The book is written in what? Mathematical language. And the symbols are triangles, circles, and other geometrical figures, without whose help it is impossible to comprehend a single word of it, without which one wanders in vain through a dark labyrinth. And these are all statements of his. Mathematics is the language in which God has written the universe. And believe me, if I were again beginning my studies, I should follow the advice of Plato and start with mathematics. I think that in the discussion of natural problems, we ought to begin not with the scriptures, Now you see why they put him in prison, right? But with experiments and demonstrations. So you can see what happened. Here we had this man, and he was one of the first to propose that math and experiments is what it's all about. And you're going to see that with a pendulum, especially. We do lots of experiments, and they still cannot explain the mechanism of a pendulum. I mean, what is a pendulum? There's this here. That's a pendulum, my magic one. I mean, how difficult can it be? Here, just a little stick moving back and forth, maybe with a plumb bob at the end. Yeah, we know everything about it. I mean, as far as the description, how fast it goes, this and this and that. We know everything about the pendulum except why, what causes it to move. And this comes all the way from Galileo. Galileo saying it's all math and experiments. That's science. That's physics. And he forgot about the explanations, about the causes, the mechanisms. What causes all these things to move out there? How does Mother Nature do all these magic tricks? That's what we forgot, okay? That's what we sidestep. And what they were looking at with a pendulum was this thing about the inside track. You have the Earth going around the sun, and you have, Mars going around the sun. And so they figured out, well, if you're on the inside track, you got a shorter orbit, well, you're going to go faster than a guy who's got to go a long time around. So Galileo, they sensed this intuitively. You didn't need to be a genius to know this. But of course, a lot of people were so ignorant in those days that these guys were geniuses in comparison to them. So you have people like Galileo, they stood up because they said, I think the Earth goes faster than Mars. Well, no kidding. Yeah, because one's on the inside track, the other one's on the outside track. And so this is how they came out with this experiment with the pendulum, because it gave them an insight into this. This is what they were trying to get to. They were trying to look at how the planets moved. Remember, Galileo had one of the first to use a telescope in a way that he could observe things that he could later describe to the masses out there. He was the one-eyed in the land of the blind. And so he looked at the Galilean moons of Jupiter, the 4 moons, right? And he discovered things. Like Columbus discovered America. Did Columbus explain America? Did he invent America? No, he just bumped into it and called, I discovered America. And even that's be a challenge. But Galileo's similar. He just looked and said, I found 4 moons of Jupiter. He couldn't explain anything. And then he found a pendulum. He started working with those. And he says, here's the pendulum. I can describe it for you. I have all the relations. Yeah, but you don't know why it moves like that. What causes it to move like that? That's where he failed. That's why it wasn't science, because that's what physics is about. Explaining the causes, why it behaves that way. Okay? What's causing it to behave that way? Okay. So Galileo began playing around with pendulums as early as 1602. He was still quite young in those days. He was about to enter I think he had already entered as a professor at the University of Padua. And so he started running this experiment with pendulums, and he said, look, it's so strange because, if you look at the amplitude of 2 pendulums going side by side, and one has a short amplitude, the other one has a long amplitude, they still move at the same time. So they keep time in the same way. As long as the weight and the string length is the same, if you let go of them, one has a greater angle, it'll move faster than the other one, but they'll both be synchronized. And so he didn't answer why. He just said, it is so. So it's different to say it is so and to tell you why, how come. Okay, so let's distinguish those 2 things. Okay, he went in there and he said, well, what if I replace these two angles, and I just make them the same angle, but I change the weight. And so now he put more weight on one side and less weight on the other. In this case, we're illustrating that with 2 balls versus 1 ball, okay? And you can see that even though the angle is the same, the rate is almost exactly alike. In fact, it should be exactly alike if you knew the exact weights of all these things, right? And they had the same distance and so on. Okay, so you say, okay, it's strange. That sounds counterintuitive, that you would think that the heavier weights would move slower, right? And that wasn't the case. They moved exactly at the same rate. Okay, so what was next? Well, he said, what if we changed the string length? And so now they changed the string length, and now they did notice something very strange. Now that did change for the first time, the rate at which they oscillated. And so they said, okay, the weight doesn't change it, and the angle doesn't change it, the amplitude doesn't change it, but apparently the string length does. Okay, so he had a description. he looked at that. That's just intuition. That's what he sees in front of it. Observer stuff, gawking, and you just describe what you see, and you get a Nobel Prize. I get the Nobel Prize in pendulums. Why? Because I was the one who discovered that the amplitude and the weight doesn't change anything. What changes the rate is the length of the string. Okay, so he gets 100 points for that. And so he should get a Nobel for that, for discovering something about the pendulum, a description about the pendulum. Is that what science is about? Is that what physics is about? Bumping into the wall and say, hi, I discovered the wall. But yeah, you still have the paint on your nose. I'm the one who discovered the wall. I get a Nobel Prize for the wall because I'm the discoverer. And I mathematized it. I can tell you at what speed I hit the wall, how big it was. You can describe it any way you want. You get a Nobel for this, for describing. Okay, but we went on to this. He went on to this. Galileo used his knowledge, his extensive knowledge of pendulums, to create the pendulum clock. He didn't create it. He designed it, gave it to his son, who died a few years later, died prematurely, more or less. And his son was constructing this device when he died before he was able to finish it. But they have constructed it today, and this is what it looks like. So if you want to see how it works more or less like this. There it is. Okay, and you can see each one of those tick marks. Okay, is caused by the pendulum swinging back and forth. Okay, so this was what Galileo had in mind. This is what he invented. Is this science, or are we talking about technology here? So yeah, Galileo observed, and because observed without understanding anything of the causes, the whys, the mechanisms, he was able to build a device. We call this technology. So he developed technology based on description, but so far we have no understanding of why the pendulum goes back and forth. And yeah, this is, by the way, this is a gravitational clock. And just in case you didn't notice, let me make that specifically clear. Okay, you can see this moving back and forth. Okay, but while it moves back and forth, you see that the weight is falling. So I put it in fast motion just so you would see that. Okay, you see how it's dropping the weight that's there? That's what's driving the mechanism. Okay, if you didn't have that weight there, you would not have perpetual motion. Okay, so if you think that it's gravity moving that and then it moves forever, well, no, it's got something that allows it to move. And in this case, it's that weight, which is a weight thing, not a mass thing. It's got nothing to do with mass. It's got to do with weight, meaning the force of gravity. Okay, so it's a gravitational clock, by the way. Okay, just wanted people to be aware of that. Okay, so, and by the way, Christian Huygens later on, I think it was 1665, he made the first really practical pendulum clock. Okay, and from there, again, time was very closely associated with the pendulum. They wanted to control time, and here was one of the first devices that really they were able to, or you could say the first clock, right? That in which they were able to really measure time to any measure of accuracy. Okay, it was the pendulum clock. This was the real. Before that, they had water clocks and clepsydras. The drop of water. And they replaced that with the pendulum clock, which was a little more controlled. And of course, from then on, clocks were improved over time. And by the time you get to the 19th century, you have this fellow, and he uses this pendulum to tell you that the Earth is rotating. Okay, that's Foucault. And what you see is that the sweeping of that pendulum changes angles simply because the Earth rotates. Okay, so he was able to show that without staying outside of the Earth, being inside the Earth, you could show that the Earth rotates with this little device. Okay, what did they all miss? From Foucault before and Foucault onwards, all of them. What did they all miss? This is what Galileo missed. Okay, this was the cause. We're going to put the cause of the pendulum. What causes the pendulum to behave the way it does? Okay, and there you see it. Okay, we put it on top of the Earth. Okay, Galileo there with his two little pendulums. Well, every atom of each one of those pendulums is attached to every atom on Earth. I just put the main ones because that goes to the center of the Earth, which is the center of gravity of our planet. It's a sphere. Okay, this also shows that it's got to be a sphere, otherwise the pendulum wouldn't work. And yes, if every atom of the pendulum is attached to every atom on Earth, specific and stronger as you move towards the center, well then, yes, this is the reason that there's a physical influence from the Earth on those two pendulums. Okay, so this is what they missed. What they missed is the ropes, the stuff that they could not see or touch. And clearly, you're not going to be able to discover the ropes through see or touch. You know, you can't see or touch the ropes. Okay, here again. You know, I say pencil, let go of it, falls to the earth. Again, repeatable. You always have to make it repeatable for it to be scientific, right? So we do it at least 2 times, and that's called repeatable. Also falls to the earth. I guess I proved my point. Okay, but the issue is there's nothing here and there's nothing here, other than air, right? But I mean, air is not. It's not air that causes gravity. Okay, so what is pulling? What is pushing on the pencil? What came in contact with the pencil? Okay, and the same with the pendulum. I mean, if you have the pendulum moving back and forth, I don't want to hypnotize you, but you know, if you move this back and forth, why does it cling and move back and forth? Well, again, because every atom of that pendulum is stuck to every atom on Earth, primarily towards the center is the strongest force, right? And so, yeah, it moves and it comes back because it's trying to get to that center. And eventually, if you let it stay there for 2 hours, it'll stand there and point to the center of the Earth. See how simple it was? And the only way you're going to figure that out is if every atom of the pendulum is bound to every atom on Earth. If it's not physically bound, why would it point in the direction of the center of the Earth? And why would it eventually stop at that point, right? After swinging. And then the other issue is if you don't explain it with some kind of pull, some kind of attachment, in this case, every atom being connected to every atom on Earth of the pendulum, right? What are you going to put in there? Spirits? Energy? Is that what we're going to put in there? We're going to call it the mass. What is the mass? Oh yeah, that's right. We determine mass by weighing.